The Group 5A Elements by Kate Schillinger, Ava Weiss, Lauren Angus, and Peter Lee.
First, let's consider the metallic character. As we move down the group, the elements become more metallic in nature. Nitrogen and phosphorus are at the top, are nonmetals, and then arsenic and antimony are metalloids, and bismuth at the bottom is classified as a metal. The shift towards metallic character occurs because as atoms get larger, the nucleus has a weaker hold on the outer elements, making it easier for these elements to lose electrons and exhibit metallic properties. Next is atomic radius. It also increases as we go down the group. With each element down, an additional electron shell is added, making the atoms progressively larger. The large atomic size is a key factor influencing other properties we'll discuss, as the outer electron is farther away from the nucleus and experiences more electron shielding. Electron affinity is another property that decreases as we go down group 15. Electron affinity reflects the element's tendency to attract additional electrons, and because of the atomic size down the group, the attraction between the nucleus and any other added electrons becomes weaker. As a result, elements at the top, like nitrogen, have a higher electron affinity compared to elements at the bottom, like bismuth. Ionization energy, which is the energy required to remove an electron, also decreases down the group. Due to large atomic size and weak attraction between the nucleus and outermost electrons, it takes less energy to remove an electron from the atom slower in the group. Next, let's move on to melting and boiling points, as we see an increase down group 15. Heavier atoms and more complex structures lead to stronger intermolecular forces, particularly van der Waals forces, which require more energy to overcome. Therefore, elements lower in the group have higher melting and boiling points. Reactivity in group 15 decreases down the group. Nitrogen at the top is highly reactive under certain conditions, but as we move down to heavier elements such as bismuth, reactivity decreases. This is due to a weaker effective nuclear charge on the outermost electrons, reducing their tendencies to participate in chemical reactions. When we look at oxidation states, we observe that stability in +5 oxidation states decreases as we move down a group, whereas +3 oxidation states becomes more stable. This is due to what we call an inner pair effect, where heavier elements tend to retain their s orbital electrons in non-bonding states, making the +3 states more stable than +5 in elements like bismuth. Finally, common oxidation states from group 15 elements range from -3 to +5. Because they have 5 valence electrons, they can achieve a full outer shell by either gaining, losing, or sharing electrons, which gives them a range of possible oxidation states.
About reactivity of group 15 elements, let's start with nitrogen. Nitrogen is highly stable as a diatomic molecule, N2, due to its triple bond, which requires a lot of energy to break. This makes nitrogen relatively inert at room temperature, although it becomes reactive at higher temperatures, where it forms compounds like ammonia and nitric oxide. Phosphorus typically exists in the form of P4 molecules, which has a strained P4 tetrahedral structure, where the bond between phosphorus atoms are single bonds, so it's highly unstable and reactive. Phosphorus has several allosotropes, such as white, red, and black phosphorus. Phosphorus atoms are larger than nitrogen atoms, so they have more diffuse electron clouds. This means the bonding electrons in P4 are farther from the nucleus and experience less effective nuclear charge, making the P4 molecules less stable and more reactive. Nitrogen is highly electronegative and less likely to react with elements that it cannot strongly bond with. Phosphorus, being less electronegative, is more willing to share or transfer electrons, increasing its reactivity with a broader range of elements. Arsenic, antimony, and bismuth are mostly found in the metallic form. Arsenic and antimony have less tendency to react with oxygen compared to nitrogen and phosphorus, but they can still form oxides, sulfides, and compounds with halogens. Arsenic is less reactive than phosphorus and nitrogen, but more reactive than antimony and bismuth. It typically reacts under specific conditions, such as elevated temperatures rather than spontaneously like white phosphorus. Bismuth at the bottom of the group shows the least reactivities due to its low electron activity and metallic properties. Bitumen is relatively inert, which is why it's often used in low toxicity applications like certain medicals. So in summary, the reactivity of phosphorus is greater than nitrogen and greater than arsenic and greater than antimony and greater than bitumen. This trend is due to an increase in atomic size, a decrease in electron activity, and a greater metallic character.
Important chemical reactions of the group. For nitrogen specifically, the formation of ammonia through the Haber process involves combining nitrogen gas with hydrogen gas under high temperature and pressure, using a metal catalyst, typically iron, to produce ammonia, according to the chemical reaction as seen. Also, nitric acid is formed through a process called the Oswald process, where ammonia is oxidized to nitric oxide, and further oxidized to nitrogen dioxide, which is finally absorbed in water to produce nitric acid. For phosphorus, any phosphorus rock can be used for the production of elemental phosphorus. Crust phosphate rocks and sand react at 1,700 Kelvin to give phosphorus oxide, which can then be reduced. Additionally, the wet process uses sulfuric acid to treat phosphate ores that contain minerals such as calcium hydroxyapatite or fluoride apatite, as exemplified in the balanced chemical reaction to produce phosphoric acid.
For arsenic, arsenic is stable in dry air, but the surface oxidizes slowly in moist air to give a bronze tarnish and finally a black-like covering to the element. When heated in air, arsenic ignites arsenic trioxide, actually tetraarsenic hexaoxide. This is accompanied by phosphorescence under some conditions. When heated in oxygen, arsenic ignites in oxygen to form arsenic pentoxide, which is actually tetraarsenic decaoxide. Arsenic is mainly obtained by heating arsenic-containing sulfides. Arsenic reacts with fluorine to form the gas pentafluorine arsenic fluoride. For antimony, solutions of antimony chloride react in hydrochloric acid when added to excess water to form the basic white insoluble salt, antimony oxychloride. Antimony reacts with aqueous ammonia to precipitate white antimony hydroxide. Under moderately acidic conditions, it precipitates with H2S and precipitates red Sp2S3. In the presence of hydrochloric acid, either aluminum or iron will reduce the antimony ion to antimony metal, which will be deposited as black particles.
For bismuth, when combined with air, it forms trioxide bismuth 3 oxide. The flame is bluish white. When reacted with water at red heat, bismuth reacts to form trioxide bismuth oxide. When reacted with halogens, for example fluoride, it forms pentafluoride bismuth fluoride. It too can react with chlorine, bromine, and iodine to form the respective trihalides. Additionally, when reacted with acids such as sulfuric acid or nitric acid, it forms it produces bismuth 3 chloride.
Group 5A elements have many similarities and differences to other groups. Other elemental groups are not as stable as the Group 5A elements, and their covalent bonds are not as strong. Group 5A is closely related in properties, while other groups such as the Group 7A elements are not related in their elemental properties. Group 5A starts with a gas, just like groups 6A, 7A, and 8A. Like the other A groups, 5A elements follow a pattern in their electron configuration and shape.
The applications of group 5A elements in life. As you can see, these elements exist all around us. For nitrogen specifically, it can be found in fertilizers to enhance crop growth, food preservation to extend shelf life in packaging, industrial uses such as explosives and carcinogens, and medical applications such as cryotherapy and anesthesia. For phosphorus, it can also be found in fertilizers to promote root development, detergents to soften water for better cleaning, and food additives as preservations and flavor enhancers. Arsenic specifically can be found in wood preservation to prevent rot and insect damage, semiconductors for electronics, and glass production to improve clarity and reduce bubbles. Antimony can be found in flame retardants to reduce flammability in materials, and alloys to enhance properties of lead in batteries. Lastly, bismuth can be found in pharmaceuticals as an active ingredient in digestive medications, cosmetics as non-toxic pigment in products, and lower temperature soldiers in electronics.
Well, there are many fun facts about the Group 5A elements. Here are a few that we thought were very interesting. Phosphorus was originally discovered by German alchemist Henrik Brandt on his quest to find the mythical substance known as the Philosopher's Stone. The Philosopher's Stone was thought to guarantee immortality and turn any material into silver or gold. He believed urine was the key ingredient to create the stone and discovered phosphorus in the urine.
Nitrogen was first discovered in 1772 by Scottish scientist Daniel Rutherford when he removed oxygen from air and noted that the remaining gas couldn't support life or combustion. He called it burnt air.
Bismuth has a unique iridescent appearance when oxidized, creating a beautiful rainbow-colored crystal.
Antimony has a unique properties called antimony's tail. When it is melted and cooled, it can form distinctive snowflake-like crystals.